On October 15th, behind the Sun, 3 objects appeared alongside 3I-ATLAS that were never supposed to be there. The Sun, which has been uncharacteristically quiet for weeks, woke up violently and erupted not once, not twice, but thrice, as each of these objects crossed past its path. Everything was caught on camera. The movement was precise, unnatural, and too perfect to be chance. And yet, silence. No official explanation. No front-page headline. Typical of a deliberate cover-up, or maybe they are hoping no one notices. Well, they're wrong. Tonight we journey through the forbidden data, and what we uncover at the end will give you a glimpse of the most dangerous secret in astronomy right now. If these mysteries continue to keep you awake at night like they do me, make sure to tap like and subscribe so you're here for every twist as it happens in real time. Let me know in the comments where you're watching from, what time it is on your clock, and tell me straight, do you think we're being told the whole truth about these mysteries? And if you want to push this conversation even further, share this video on X, Facebook, Reddit, or even just your group chats. This community exists because of you, and your support is what lets us keep pulling on threads the world would rather ignore. Part 1. The Impossible Clip. Imagine you're watching a live stream on an ordinary Tuesday afternoon. The Sun appears on your screen, peaceful and distant, a golden sphere suspended in the digital dark. But then something shifts. 3 objects, dark, unidentified, moving with precision, glide across the frame in rapid succession. Each one arrives, and moments after each passes, the Sun erupts. Not once, not twice, 3 times. The Sun had been unusually quiet for weeks, but the moment these objects cross its path, it wakes up violently, as though shocked awake by an electric charge. This is not speculation. This is what amateur astronomer Tiago, known online as Dobsonian Power, recorded and shared with the world this week, and it has shattered our comfortable assumptions about what can and cannot happen in our solar system. The images come from LASCO, the Large Angle and Spectrometric Coronagraph, instruments aboard the Solar and Heliospheric Observatory, or SOHO, a satellite that has watched the Sun without break for 30 years. These are not blurry smartphone captures or creative interpretations. These are official data streams, the same images that NASA scientists review every single day. What Tiago observed was a phenomenon that should not exist according to our current understanding of orbital mechanics and solar physics. The 3 objects he documented were aligned. They moved in formation. They were not random cosmic debris tumbling toward our star. Their trajectories suggested intention. Their timing suggested coordination. When Tiago posted his findings, he called them companions or dark stuff following 3I-ATLAS, the interstellar object that arrived from beyond our solar system in late 2024. The online astronomy community erupted. Here is where the story becomes uncomfortable for mainstream science. The statistical probability of 3 independent objects triggering 3 solar events in sequence is so vanishingly small that if you tried to explain it to someone using conventional probability, they would laugh. We are not talking about unlikely. We are talking about the kind of unlikely that makes you stop and reconsider whether something else is happening beneath the surface. 3 objects, 3 explosions. The pattern is too clean. The timing is too precise. The coincidence is too perfect. When you work in any field that deals with data, you learn that patterns like this do not occur by accident. They occur because something is driving them. Yet silence followed. No NASA press conference. No ESS statement. No official acknowledgement from any major space agency or research institution. The institutions tasked with understanding our solar system simply did not respond. In a world where every discovery is amplified and celebrated, where detection of distant exoplanets and gravitational waves generates immediate headlines, the images of these 3 objects passed through official channels and encountered what can only be described as institutional radio silence. This absence of commentary becomes its own statement, raises its own questions. Why would the organizations that see everything the Sun does, that employ thousands of scientists, remain completely quiet about an event that contradicts our fundamental understanding of what is possible in near-solar space? Independent observers were watching too. Skywatchers on X named Night Monkey and Tobazil, both seasoned in identifying celestial phenomena, reported seeing fast-moving points of light near Gemini and throughout all sky surveys. Their observations aligned with Tiago's timeline. Multiple independent sources, different equipment, different vantage points, all reporting the same phenomenon within the same window of time. When one observer reports something unusual, you catalogue it as curiosity. When 5 observers report the same thing independently, you have corroboration. When institutions ignore corroboration, you have to ask what they're afraid of. The motives for silence are not difficult to imagine. Discovery of artificial objects in near-solar space would demand a complete restructuring of how we understand our place in the universe. It would transform overnight from a scientific curiosity into a geopolitical crisis. It would create legal questions, military questions, existential questions that no government or scientific body is prepared to answer. There is safety in silence. There is protection in pretending nothing happened. But silence also creates a vacuum, and a vacuum invites speculation, conspiracy, and the inevitable flood of misinformation. The smarter approach, the more honest approach, would be to acknowledge what was observed and investigate it openly. Instead, we are left with a question that the official scientific community refuses to ask. Could this be the first publicly recorded kinetic intervention in solar physics? Could we be watching, in real time, humanity's first contact with non-human intelligence? These are the questions that keep us awake at night, and they begin with 3 objects and 3 explosions that no one in power is willing to discuss. Part 2. Pattern recognition or cover-up. Probability is a harsh mirror. When you hold it up to the events surrounding 3I-ATLAS, something becomes immediately apparent. If 3 separate objects, each entering near solar space, each independently triggering solar eruptions, if all of this were purely random, purely coincidental, the odds would be roughly equivalent to shuffling a deck of cards and drawing the ace of spades 500 times in a row. It is not impossible. It is just so unlikely that suggesting it happened by chance becomes a statement of either profound ignorance or deliberate denial. The human brain is wired to recognize patterns. This is how we survived as a species. A pattern that could be predator or prey gets our attention. A pattern that repeats gets our investigation. 3 explosions following 3 passages is not background noise, it is signal. But here is where institutional science pulls back and retreats into defensiveness. Scientists will tell you that correlation is not causation, that extraordinary claims require extraordinary evidence, that we must maintain healthy skepticism. All of this is true, all of this is important. But healthy skepticism can become pathological when it insists on ignoring evidence that challenges our existing models. When we reject data simply because it conflicts with what we thought we knew, we are not being scientific. We are being dogmatic. We are protecting our theories instead of serving the truth. Sabine Hossenfelder, a physicist with decades of credibility, has warned specifically about this tendency. She has said publicly that rejecting the possibility of artificial origin without rigorous investigation would be the single biggest mistake our civilization could ever make. Not a mistake. The mistake. The one that matters most. The timeline of events is crucial here, so let us walk through it carefully. The sun had been unusually quiet in the weeks leading up to Tiago's observations. Solar activity was subdued, as if the star itself was sleeping. Then 3I-ATLAS approached, bringing with it these 3 companion objects. The moment they passed near the solar surface, the star awakened. The eruptions came rapid fire, like a cascade of responses, as though the sun was reacting to something, defending itself against something, or perhaps being triggered deliberately by something. Historical parallels are instructive. When military forces discovered the unexplained aerial phenomena problem in the 1940s and 50s, they did not immediately declassify everything. Instead, they classified it, compartmentalized it, and maintained institutional silence while investigating privately. We now know that government agencies and military branches were tracking anomalous objects and events continuously, and they told the public essentially nothing. The secrecy lasted 70 years. Why would it be different now? Independent confirmations have continued to arrive. Night Monkey documented fast-moving signatures in multiple all-sky surveys. Tobozil tracked objects that displayed motion inconsistent with standard comet behavior or orbital debris patterns. Other amateur astronomers, working with publicly available data from SOHO and other solar observation platforms, have identified additional anomalies that the mainstream astronomy community has not addressed. This is not a single observer making wild claims. This is a growing body of independent documentation pointing towards something real, something measurable, something that exists in our data but has not been integrated into our official narrative about what is happening in near-solar space. The closer we examine the facts, the more difficult institutional silence becomes to justify. Yet the counter-argument deserves respect. Space agencies often do wait for verification before making public statements. They do face legitimate pressure to ensure that anomalies are genuine before broadcasting them to the world. The risk of crying wolf, of announcing a discovery that turns out to be an instrument artifact or a misinterpretation of data, is real and serious. Scientific credibility is earned slowly and lost quickly. Rushing to conclusions, even in the face of compelling patterns, can undermine the authority of institutions that we need to trust with critical information about our world and our solar system. This is the genuine tension at the heart of the matter. On one side, institutional caution and the scientific method. On the other side, transparency and public access to information about events that may have profound implications. Both values matter. Both create legitimate demands. Neither can be fully satisfied without compromising the other. But here is what we cannot do, and what we seem to be doing anyway. We cannot simply pretend the anomalies do not exist. We cannot dismiss independent observations because they make us uncomfortable. We cannot maintain silence while evidence accumulates, because silence maintained long enough becomes complicity. It becomes a choice. It becomes institutional corruption masquerading as prudence. The pattern is there. 3 objects, 3 explosions, 3 independent observers documenting the same thing within the same time frame. The evidence is not equivocal. It is not subtle. It is not hidden in noise or distortion. It is visible in our own data, waiting for someone in power to simply acknowledge that it exists. And when we move from this question of timing and correlation to the actual nature of the light itself, the mystery deepens into something far stranger. We need to examine polarization and what polarization tells us about the composition and origin of 3I-ATLAS itself. Part 3. The Polarization Paradox. Light travels as a wave, and like any wave, it oscillates. In normal circumstances, that oscillation happens in all directions perpendicular to the direction of travel, like a stone dropped into still water creating ripples in every direction. But when light encounters dust, ice crystals, or complex surfaces, something remarkable happens. The wave oscillation becomes organized. It begins to oscillate preferentially in one direction or a few directions. We call this polarization, and it is extraordinarily sensitive to the physical properties of whatever the light has bounced off or passed through. Scientists have used polarization analysis for decades to understand comets. They know what patterns of polarization to expect from certain types of dust particles. They know how ice grains polarize light differently than silicate minerals. They have built a catalogue of normal responses, a baseline of how ordinary comets behave when sunlight passes through their dusty envelopes and reflects back toward Earth. 3I-ATLAS violates this baseline so severely that the researchers who analysed it were forced to publish their findings under headline titles that screamed with uncertainty and concern. The paper from Gray and colleagues on ARSF documents extreme negative polarization in 3I-ATLAS, reaching values of -2.7% on curves where most comets cluster between 0 and 2%. This is not a minor deviation. This is not within normal variation. This is a pattern so unusual that existing models of dust and ice behavior struggle to explain it. The polarization inversion angle is wrong. The phase curve does not match what we expect. The whole optical signature points to something that should not be there if 3I-ATLAS is indeed a normal comet composed of ordinary ice and dust. Imagine trying to identify a human by their fingerprint, and the fingerprint does not match any database, any known type. The ridges flow in the wrong directions. The patterns do not conform to human anatomy. You would immediately suspect either that the fingerprint is fake, deliberately fabricated, or that you are dealing with someone whose biology is fundamentally different from the human norm. This is what the polarization data is telling us. Either 3I-ATLAS has a surface composed of materials we do not commonly observe in the solar system, or its structure and texture are unlike anything we have catalogued before. The speculation naturally follows. If not ordinary dust, then what? Exotic ices, engineered materials, surfaces designed to have specific reflective properties. The mainstream response has been to propose what researchers call a dust-rich gas-poor comet model. This suggests that 3I-ATLAS is composed almost entirely of solid material with very little gaseous component, and that the dust itself is larger and denser than typical comet dust. This would suppress the expected spectral signatures we normally associate with comets, while potentially explaining some of the polarization anomalies through the sheer size and density of particles rather than their chemical composition. This is a reasonable hypothesis. It is scientifically sound. It is also, conveniently, a hypothesis that does not challenge our existing cosmology. It keeps 3I-ATLAS firmly in the category of unusual but ultimately natural phenomenon. Avi Loeb, the astrophysicist who has been most willing to consider artificial origins, assigns this natural explanation a likelihood of roughly 4 out of 10, which means he assigns the alternative, something more exotic, something more deliberate, a likelihood of 6 out of 10 or higher. When you hear those numbers, you should pause. A scientist of Loeb's standing saying that non-natural origins are more likely than natural ones is not the same as saying he believes in aliens. It is not the same as claiming certainty. But it is a statement that the anomalies are so severe, so contrary to expectation, that the conventional explanation is actually the minority position among experts willing to engage with the data honestly. This is the pattern repeating across every layer of analysis. The data points elsewhere, the model strained to contain it, the institutions maintain silence, and all the while, the light bends in ways we do not fully understand, revealing a surface or a structure that does not fit our categories. What polarization shows us is a physical property of 3I-ATLAS that contradicts our assumptions. But the real smoking gun, the evidence that truly makes scientists uncomfortable, lies not in how light bends around this object, but in what elements compose it. We need to look at the spectrum, at the chemical fingerprints that 3I-ATLAS is broadcasting into space. Part 4. Chemistry of the Outlier. Spectroscopy is essentially cosmic forensics. When light passes through or bounces off matter, each chemical element leaves a signature, like a fingerprint burned into the spectrum. Nickel creates a specific line. Iron creates another. Cyanide creates yet another. Scientists have catalogued these signatures for every element, and they can look at a spectrum and identify exactly what is out there, how much of it exists, and how it is distributed. When the Keck Observatory, one of the most powerful telescopes on Earth, pointed at 3I-ATLAS and captured its spectrum, something unprecedented appeared in the data. Nickel emission lines were detected. This is not surprising. Nickel exists in comets, but here is where it becomes interesting. The iron lines were not there, or rather, they were suppressed to an unusual degree. The nickel-to-iron ratio in 3I-ATLAS is orders of magnitude higher than in any known comet. It is not just unusual, it is contradictory to everything we know about how solar system objects form. The implications become sharper when you consider the cyanide ratios. Cyanide emission is standard in comets. It appears consistently across different objects, but in 3I-ATLAS the nickel-to-cyanide ratio is enormous. It is so extreme that if you tried to propose it as a natural occurrence, without additional explanation, peer review would laugh you out of the room. Yet the data exists. The Keck Observatory collected it, researchers have published it, and the mainstream astronomy community has largely ignored it or explained it away using the dust-rich model. But here is where industrial chemistry enters the conversation, and things become genuinely unsettling. Nickel carbonyl is a compound that has precisely one major terrestrial use. It is used in industrial processes, specifically in metallurgical cycles, to extract and purify nickel on industrial scales. The compound forms when nickel is exposed to carbon monoxide under specific conditions. It is not commonly found in nature. It is engineered, it is manufactured, and when you see high concentrations of nickel separated from its normal iron companions, when you see ratios that contradict natural formation, when you see combinations that point toward industrial metallurgy, you have to at least ask the question, could something be separating these elements deliberately? The critic's response is immediate and logical. Natural nickel carbonyl pathways do exist. In the interstellar medium, carbon monoxide exists, nickel exists. Under the right conditions, the right temperatures, the right pressures, naturally occurring processes could produce these compounds. It does not require technology. It does not require intelligence. It requires only chemistry and time. Loeb himself acknowledges this. ranking the possibility of artificial origin at 4 out of 10, suggesting that natural pathways remain plausible explanations. This is important. This is where we must be rigorous. We cannot see a chemical anomaly and leap immediately to aliens. That is not how science works. That is how confirmation bias works. We must hold multiple hypotheses in our minds simultaneously. Natural metallurgical processes could explain the nickel ratios, but so could intentional separation and processing of materials. Both remain possible. Both remain supported by the data. The question is not whether one is true and one is false. The question is which one is more probable, and what additional evidence we would need to lean one direction or the other. This is where institutional silence becomes particularly frustrating. Because the next step in investigation is obvious. We need more spectroscopic data. We need better resolution. We need to understand not just what elements are present, but where they are distributed within 3I-ATLAS, and in what physical configurations they exist. We need to examine the isotopic ratios, which can tell us whether these elements came from the interstellar medium or from processed stellar environments. We need to conduct comparative analysis with every other interstellar object we have ever observed to see if these ratios appear anywhere else, or if 3I-ATLAS is unique. These are all reasonable investigations that any well-funded research team should be undertaking right now, but few resources are being directed toward them, few papers are being published, few discussions are happening at major astronomy conferences. It is as though the scientific community has collectively decided that the question is not worth asking. And when the scientific community collectively decides that, you have to wonder what they are protecting. The chemistry points towards something artificial, or at least something fundamentally anomalous. But chemistry alone does not settle the question. We need to look at the physical structure of 3I-ATLAS itself, at the raw images that have been captured of its nucleus, because what we see there opens an entirely new realm of possibility and speculation. Part 5, The Stingray and the Pyramid. Raw imagery from the Gemini Observatory tells a story that extends beyond spectroscopy and polarization into territory that makes skeptics profoundly uncomfortable. The nucleus of 3I-ATLAS, when examined in the highest resolution images available, does not appear as the irregular potato shape typical of most comets. Instead, observers have reported seeing what they describe as a stingray-like configuration, with hints of structure and geometry that deviate from randomness. Some viewers, leaning heavily into speculation, have identified what they interpret as stepped pyramid or ziggurat formations. Now, before we proceed, let us be absolutely clear about what we are looking at. Images from telescopes are subject to pixelation. They are subject to distortion from atmospheric turbulence. They can contain artifacts from the imaging process itself. The human brain is a pattern recognition machine that has been trained by hundreds of thousands of years of evolution to see intention and design even where none exists. We see faces in clouds. We see conspiracies in statistical noise. We see meaning in randomness. This is not a weakness necessarily. It is a feature of how we survive, but it is also a source of profound error when applied to astronomical data. And yet, the question of morphology matters. A perfectly spherical asteroid would indicate something unusual. An asteroid shaped like a perfect cube would indicate something even more unusual. Shape carries information. Shape can reveal formation process. Shape can reveal intentional design if design exists. The debate about 3I-ATLAS's shape is not abstract. It is concrete. Multiple observers using different telescopes at different times have reported geometric elements that recur in the images. These are not solitary reports from crackpots or conspiracy theorists. These are independent observations from serious amateurs and professionals who are willing to stake their credibility on what they believe they see. The question becomes not whether these observers are lying or hallucinating, but whether they are interpreting ambiguous data through a lens of expectation and desire to find anomalies. The broader context becomes relevant here. In early 2025, reports circulated of a high-level United States military meeting held at Quantico involving generals and operators from the Naval Radio Telescope facility. The official story, to the extent any story exists, suggests routine briefings on space weather and solar threats, but the timing is suspicious. The meeting occurred immediately after the most intense period of observations of 3I-ATLAS. The meeting involved radio telescope operators who would have access to non-optical data about the object that is not available to civilian astronomers. The meeting involved high-ranking military personnel, suggesting either an unusual level of concern or an unusual level of awareness. None of this is proof of anything. None of this confirms that objects are artificial. But none of it is coincidental either. It is part of the pattern. It is another thread in the tapestry that suggests institutions are taking this phenomenon more seriously than their public pronouncements would indicate. Why shapes matter is worth dwelling on. In nature, most objects form through random processes. Gravity pulls material together from all directions, creating roughly spherical bodies. Solar wind sculpts tails. Outgassing creates jets. These processes generate shapes that are complex but fundamentally arising from symmetrical forces. But engineered objects, objects deliberately constructed, tend to show different patterns. They show angles. They show repeating geometries. They show configurations optimized for specific purposes. They show design. When observers report stingray shapes and pyramid formations in images of 3I-ATLAS, they are asking the question whether this object shows the properties of an engineered structure or a naturally occurring body. The data is too pixelated and noisy to reach certainty, but the patterns reported are too consistent across multiple observers to dismiss as hallucination. We are in territory where truth requires better data, higher resolution images, and closer observation. And as we move from what we can see directly to what the object might actually be doing, we must confront the possibility that 3I-ATLAS is not travelling alone because it has companions travelling with it for a reason. Part 6. Guardians or Assassins. The three objects that Tiago documented preceding the solar eruptions invite a question that borders on science fiction, until you remember that these objects are real, documented in official data, and contradicting every model we have for what can happen in near-solar space. If these objects are travelling with 3I-ATLAS deliberately, if they are somehow associated with it or controlling it, then what are they doing? What is their purpose? Tiago himself has speculated that they might be companions, that they might be fulfilling some function relative to the main body. But what function? The most obvious interpretation is protection. Perhaps these are guardian objects positioned to defend 3I-ATLAS from something, to shield it from some danger or threat inherent in passing through the inner solar system. The analogy of an escort emerges naturally. Military convoys deploy protective elements around valuable cargo. They position defensive assets to create a perimeter. They maintain vigilance against external threats. If something similar is happening here, then 3I-ATLAS is valuable cargo, important enough to warrant protection, important enough that whatever intelligence sent it is willing to deploy multiple additional objects to ensure its safety. But this is only one interpretation. The inverse interpretation is equally plausible. What if these companion objects are not guardians but attackers? What if they are positioned not to protect but to destabilize? What if they are actively working against 3I-ATLAS, disabling it or manipulating it as it passes through our solar system? In this scenario, the solar eruptions become a weapon. The companions would be using the sun's own magnetic field and energy against their target, triggering coronal mass ejections and directing them with precision. It is a shocking image, but no more shocking than the idea of protective escorts. Both are speculations. Both are based on limited data. Both invite the same question. Are we watching a cosmic convoy or a cosmic conflict? Are we witnessing the opening moves of a cosmic dogfight that has spilled into our solar system, with the sun itself as the arena and 3I-ATLAS as either the prize or the target? The hypothesis of solar eruption triggering becomes testable if we think carefully about how it would work. If the companion objects are actively triggering eruptions, we would expect to see repeated patterns. We would expect to see correlations strengthening as the objects approach and pass the sun. We would expect to see timing that is too precise to be coincidental, that shows evidence of deliberate targeting. We would expect to see asymmetries in the eruptions, perhaps preferentially in regions of the solar surface where the companion objects pass. Tiago has documented some of this. The triple cannibal coronal mass ejection that was forecasted for late January 2025 showed exactly the kind of timing correlation that would be expected if external objects were triggering the eruptions. But 3 data points do not make a conclusive pattern. We need more observations. We need time to observe how 3I-ATLAS behaves as it continues toward perihelion, its closest approach to the sun. The mechanism by which such triggering might occur is worth considering, even if speculatively. Solar magnetic reconnection is an active process. The sun's magnetic field is constantly reconfiguring itself. Tensions build, energy accumulates, release events are inevitable. But the timing and location of those releases is driven by complex dynamics that we do not fully understand. Now imagine an external object, something with an unusual charge or an unusual composition, approaching the solar surface. Its presence in the solar magnetic field could create perturbations. It could alter the field topology locally. It could provide the final trigger that converts potential energy into kinetic energy, releasing an eruption that was inevitable, but whose exact timing and location would have been different without the external perturbation. This is not magic. This is not technology beyond comprehension. This is simply the application of physics. But it requires knowledge of solar dynamics, precision, navigation, and the technological capability to approach the sun itself without being destroyed. Any civilization capable of this would be centuries ahead of us. The skeptical response points out the energy budget problems. To reliably trigger solar eruptions with anything smaller than a major celestial body, you would need to be applying enormous amounts of energy. You would need directed energy beams of staggering power or gravitational manipulation beyond our theoretical models. You would need technology so advanced that the idea of deploying it to trigger eruptions seems almost wasteful, like using a thermonuclear weapon to light a candle. And yet, this is speculation built on speculation. We do not have firm evidence that solar eruptions are being triggered deliberately. We have correlation, we have timing patterns, we have objects present at the moment eruptions occur. This is not proof, but it is precisely the kind of evidence that demands investigation rather than institutional silence. As the question of motivation and mechanism swirls around 3I-ATLAS, another pattern begins to emerge that suggests this comet is not unique. Other green comets are in our sky right now, and they are behaving strangely too. Part 7. The Silence of the Green Comets. In the months since 3I-ATLAS arrived and began displaying its catalogue of anomalies, other comets have graced our skies. These are not random visitors. They are nearby enough to be visible to naked eye observers and binocular users. They glow with the characteristic green hue caused by diatomic carbon molecules in their comas, the illuminated cloud of gas surrounding the nucleus. Comet C-2025, A6 Lemon arrived from the outer solar system. Comet C-2025 R2, Swan began its approach. Comet C-2025, K1-ATLAS, the namesake of the automated telescope system, joined the party. These are the forgotten cousins of 3I-ATLAS, and they have attracted minimal attention, despite their proximity to Earth and their visibility to casual observers. The astronomy media coverage has been sparse, the mainstream science discussion has been nearly non-existent, and when you compare the reporting on these comets to the reporting on 3I-ATLAS, an interesting pattern emerges. The focus narrows, resources concentrate, attention congregates around the most anomalous object, leaving the others in shadow. This might be perfectly natural scientific triage. 3I-ATLAS is genuinely the most anomalous, so naturally it receives the most attention. Scientists have limited time, limited funding, limited resources. They must prioritize. It makes sense to study the most interesting case. But here is what makes silence about the other green comets particularly interesting. Some of them are displaying odd behaviors. Some are exhibiting unexpected emission lines. Some are showing anomalous brightness variations. Some are displaying tail orientations that do not align with solar wind pressure models. None of this is definitively anomalous. None of this is unambiguous evidence of non-natural origin. But taken together, across multiple objects arriving simultaneously from space, the pattern suggests something worth investigating. Are these comets just naturally more exotic than usual? Are we seeing a rare cohort of unusual but natural objects? Or are they decoys? Are they accompanying probes? Are they part of a fleet following a deliberate itinerary? The question of institutional suppression versus selective science becomes relevant. In any field, some topics attract funding and attention while others languish. This is partly meritocratic. The most interesting questions get investigated. But it is also partly political. The questions that challenge existing paradigms, that make us uncomfortable, that have implications for how we understand the world, sometimes do not receive the attention they deserve. Instead, they receive institutional silence. The institutions develop unofficial policies about which questions are safe and which are not, which researchers can pursue, which topics without career damage. which findings will be published and celebrated versus which will be filtered out. This is not a conspiracy theory. This is how institutions actually function. They have immune systems. They have antibodies that attack foreign objects that threaten their core assumptions. When data arrives that contradicts those assumptions, the immune response kicks in. The comparative analysis we need to perform is straightforward. We need to examine whether any of the other green comets show the extreme negative polarization of 3I-ATLAS. We need to look for anomalous chemical ratios in their spectra. We need to check their morphology against our models of natural comet shapes. We need to search for companion objects in high-resolution imagery. We need to correlate their approaches with solar activity. If we find that multiple comets display the same suite of anomalies, then we have moved from a unique mystery to a pattern. And patterns point to causes. Causes demand investigation. If we find nothing unusual in the other comets, then 3I-ATLAS becomes even more remarkable, even more difficult to explain through natural processes alone. Either way, the investigation should happen. Either way, the silence about these objects should break, but it has not. And the longer the silence continues, the more we must wonder whether something else is happening beneath the surface, something coordinated, something that moves across all these comets simultaneously and suggests a single organizing principle. Perhaps they are linked by a broader cosmic design. Perhaps they are not random visitors at all. Part 8. The Solar Trigger Hypothesis. The Sun is not a quiescent sphere. It is a roiling dynamic engine of nuclear fusion wrapped in a magnetic field of staggering complexity. Coronal mass ejections are violent events where the Sun's magnetic field reconfigures catastrophically and ejects billions of tons of plasma into space. The mechanism is understood in broad strokes but mysterious in detail. We know that magnetic reconnection, the rapid reorganization of field lines, causes the explosions. We know that tension builds in the magnetic field and releases in sudden cascades. We know that the timescale can vary from hours to seconds, but we do not fully understand what triggers a specific eruption at a specific time. We cannot predict them with precision. We cannot control them, or at least we cannot. But something else might be able to. The empirical possibility is straightforward. When 3I-ATLAS and its companions approached the Sun, solar eruptions increased in frequency and intensity. The correlation is visible in the data. The question is whether it is causal. Causation requires more than correlation. It requires mechanism. It requires understanding how A leads to B. In this case, how could external objects approaching the Sun trigger eruptions? One possibility is electrostatic induction. Every object in space has some electrical charge, some accumulation of electrons or deficit of electrons relative to neutral. When a charged object approaches the Sun's magnetosphere, the object's electrical field interacts with the solar field. This could create localized disturbances, areas where the field topology shifts. These disturbances could propagate outward, could interact with existing tensions in the field, could provide the final trigger that converts potential energy into kinetic energy and releases an eruption. Another possibility is gravitational disturbance. While gravity from small objects is typically negligible, it is not zero. A compact, dense object approaching the Sun could create gravitational waves or gravitational perturbations that ripple through the solar interior and corona. These perturbations could alter the configuration of energy that has accumulated in the magnetic field, could shift the balance slightly, could be just enough to trigger an eruption that was already ready to occur. A third possibility, more speculative but worth considering, involves directed energy beams. If an external object possesses the capability to generate high-energy photons or particles and direct them with precision, it could potentially manipulate the solar magnetic field directly or trigger specific reconnection events through targeted energy application. Historical correlations are worth examining even if they are incomplete. Past astronomical records do show instances where small bodies passed near the Sun and were followed by unusual solar activity. But past records are imprecise and incomplete. Causation cannot be reliably established from historical data because the data quality is poor and confounding variables abound. Modern observations are more precise, but modern observations of 3I-ATLAS are limited to the past few months. The dataset is too small to establish statistical significance. We need more time. We need more observations. We need 3I-ATLAS to reach perihelion and continue its passage, allowing us to observe whether the correlations persist, whether they strengthen, whether they show patterns consistent with deliberate targeting or with natural random variation. The triple cannibal coronal mass ejection that was forecasted for late January 2025 represented 3 separate eruptions arriving at Earth in rapid succession. This kind of event is rare, it is dramatic, it draws attention. And Tiago documented that each of these eruptions corresponded to the passage of one of his 3 companion objects. Is this coincidence or cause? The statistical probability, as we discussed earlier, is extraordinarily low. But extraordinarily low probability is not the same as proof. The skeptic can always retreat to the position that an improbable event occurred and that we cannot definitively rule out chance. This is technically true, but it is also a logical position that could justify dismissing any correlation, no matter how precise, as coincidental. The testable prediction is this. As 3I-ATLAS continues its approach to the Sun, we should observe increasing solar activity if the trigger hypothesis is correct. We should see eruptions correlating with the passages of companion objects. We should see precision timing that is too clean to be random. If instead we observe that solar activity returns to normal baseline levels, if we observe no correlation between companion object passages and eruptions, if the solar system responds to 3I-ATLAS exactly as it would to any other comet, then the trigger hypothesis fails. It is vulnerable to observation. It is falsifiable. This is what makes it scientifically meaningful. But the transition from solar trigger hypothesis to broader implications requires us to consider the human and institutional dimension, to examine why these questions are being asked by amateur astronomers and outsider researchers while the establishment maintains calculated distance. Part 9. Bias, Ego, and Gatekeeping. Science is a human enterprise, and humans bring human frailties to every institution they build. We like to imagine that science operates in some rarefied realm, above politics, above ego, above self-interest. We construct a mythology where scientists dedicate themselves purely to truth, where the best ideas win through merit alone, where data always speaks and institutions listen. This mythology is comforting. It is also largely false. Academia operates on incentive structures that reward careers over truth, that reward publications in prestigious journals over careful investigation, that reward maintaining existing orthodoxy over challenging fundamental assumptions. A young scientist who wants to build a career does not ask questions that might alienate funding agencies or senior colleagues. A researcher who has built their reputation on a particular theory does not eagerly invite evidence that contradicts it. An institution that has state capital and prestige in established paradigms does not happily embrace data that undermines those paradigms. These are not features of some broken version of science. They are features of how humans actually behave when they gather into organizations and create power structures. The framework that researchers use to evaluate risk in their investigations is called Type 1 and Type 2 error analysis. A Type 1 error is a false positive, concluding something is real when it is not. A Type 2 error is a false negative, failing to detect something that is real. Science has been trained systematically to fear Type 1 errors. We have built our institutions to minimize the risk of claiming discovery when no discovery exists. We have made it easier to miss something real than to announce something false. This makes sense in contexts where false positives create genuine danger. If we conclude a medical treatment works when it does not, people die. If we conclude a structural engineering solution is sound when it is not, buildings collapse. But in basic research, in the pursuit of understanding fundamental questions about our place in the universe, this asymmetry becomes problematic. It becomes easier to ignore anomalies than to investigate them. It becomes easier to maintain silence than to ask difficult questions. Hossenfelder has warned specifically about this tendency. She has pointed out that institutional pressure to avoid embarrassment, to avoid being wrong about something so fundamental as the possibility of artificial intelligence in our solar system, has created a system where Type 2 errors are vastly more acceptable than Type 1 errors. We will happily miss first contact rather than risk announcing first contact prematurely. Historical precedent reinforces this pattern. When exoplanets were first detected, mainstream astronomy largely dismissed them. The evidence was compelling, the methodology was sound, but the implications challenged existing models so thoroughly that the initial response was skepticism bordering on hostility. It took years for the field to acknowledge that planets around other stars were not only possible but inevitable. More recently, the study of unidentified aerial phenomena has faced institutional suppression so thorough that many researchers simply will not touch the topic. Military pilots, commercial airline crews, and trained observers report events that are anomalous, that exceed known aerospace capabilities, that deserve investigation. Instead, the scientific community maintained for decades what can only be called a conspiracy of silence. No official investigation, no institutional resources, no acknowledgement that the question was worth asking. Only when military leadership themselves declassified information and demanded official investigation did academia grudgingly begin to engage. And even now, the engagement is minimal, the resources are sparse, the tone remains dismissive rather than curious. The human dimension of gatekeeping cannot be overstated. Scientific journals have editors. Editors have opinions. Editors make judgments about what papers deserve publication and what papers do not. These judgments are filtered through peer review, ostensibly an objective process where experts evaluate the merit of research. But peer review is conducted by humans with reputations, with existing theories, with stakes in particular paradigms. A paper suggesting that 3I-ATLAS might be artificial will face skepticism from reviewers whose careers are built on understanding comets as natural objects. A paper documenting anomalous polarization will be scrutinized far more carefully than a paper describing expected polarization. The system is not designed to suppress truth deliberately. It is designed to maintain quality control, but the result in practice is that heterodox ideas face higher barriers to publication than orthodox ideas. Revolutionary findings face more skeptical review than incremental findings, and in this environment, the easiest path to career success is to ask safe questions and find safe answers. What gets attention and why is ultimately a question of institutional politics and cultural momentum. When a discovery fits existing paradigms, it attracts resources. When a discovery contradicts existing paradigms, it attracts caution, and caution, when maintained long enough, becomes obstruction. The corollary is that important anomalies get buried beneath the weight of institutional inertia. They do not disappear. They remain in the data, available to anyone with eyes to see them. But they do not get the attention they deserve. They do not get the resources they warrant. They do not get investigated thoroughly, because investigating them would require acknowledging that something is fundamentally wrong with our understanding. And acknowledging that is uncomfortable. Acknowledging that means changing careers, reconsidering lifetimes of research, admitting that we got it wrong. These are hard things for institutions to do. These are hard things for individuals to do. So instead, we maintain silence. We hope the anomalies go away. We hope someone else will study them so we do not have to. We hope that if we ignore them long enough, they will stop being uncomfortable. But there is another layer to this institutional response, and it involves classified information and data compartmentalization. Government agencies have access to satellite data, to observation platforms, to sensor arrays that far exceed what is available to civilian scientists. The military tracks objects in near-Earth space with precision that amateur astronomers cannot match. Intelligence agencies monitor solar activity and coronal mass ejections with sophistication that public sources do not allow. If 3I-ATLAS and its companions represent something genuinely anomalous, something genuinely concerning, then government entities know. They know before the civilian astronomical community knows. They have detailed information that they do not release publicly. They have raw data, real-time observations, sensor streams that remain classified. And when they choose not to disclose this information, when they maintain silence, they create a situation where civilian scientists are working with incomplete data, unable to reach firm conclusions because they literally do not have access to the most important information. They're trying to solve a puzzle while half the pieces are locked in a vault. This is not conspiracy theory. This is how governments operate. They compartmentalize, they classify, they withhold information from the public and from civilian researchers. The question is not whether they are doing this. The question is what they know and why they are keeping it secret. When you combine the institutional pressures within academia, the incentive structures that reward caution, the career risks of asking heterodox questions, the gatekeeping of publication, with the classified information held by government agencies, You create a perfect environment for the suppression of genuine discoveries. The anomalies remain visible, the data persists, but the investigation remains incomplete. The discourse remains muted, the public remains uninformed, and slowly, gradually, the uncomfortable facts sink beneath the surface of public awareness. They do not disappear. They just become the kind of thing that people vaguely know exists, but nobody talks about. The kind of thing that is visible in the data, but not acknowledged in official channels. This is the function that institutional silence serves. It is not ignorance. It is active suppression masked as prudence. It is the protection of existing paradigms at the expense of discovering truth. And once you understand how this system actually works, once you see the incentive structures and the gatekeeping and the compartmentalization, you cannot help but wonder what else has been buried beneath institutional inertia. What else has been visible in our data but invisible in our discourse? What other first contacts have we failed to recognize because we were not paying attention or because we were actively choosing not to see? Part 10. The Alien Tech Debate, Reloaded. Avi Loeb stands in a peculiar position within the astronomical community. He is credentialed, he is published, he is respected, and he is willing to ask the question that others will not ask. His work specifically examining whether 3I-ATLAS might represent artificial technology is published on AF Archive, the preprint server where scientists share research before and during peer review. The paper is titled, "Is the Interstellar Object 3I-ATLAS Alien Technology?" The mere existence of this paper, written by a scientist of Loeb's standing and circulated through legitimate academic channels, represents a threshold event. The question is no longer relegated to fringe speculation. It is part of the academic record. It is something that future researchers will have to cite and address. Future textbooks, future students, future scientists will know that the possibility was considered seriously by a credible expert. This matters more than you might think. Once a question has been asked and seriously considered in academic literature, it cannot be unasked. It becomes part of the historical record. It becomes something that has to be addressed rather than ignored. The dark forest hypothesis, proposed by Liu Cixin in his science fiction trilogy, and adapted as an analytical framework by researchers considering cosmic contact scenarios, provides context for understanding why artificial objects might be travelling through our solar system unannounced. The premise is that the universe is fundamentally dangerous. Civilizations that reveal themselves risk destruction by more advanced civilizations, or by those who perceive them as threats. The rational response to this danger is to hide, to maintain silence, to avoid broadcasting one's existence. A probe or object travelling through interstellar space might be doing so precisely because it is being cautious, staying dark, minimizing energy signatures and communication. It might be reconnaissance, gathering information about our civilization without revealing itself. It might be a passive observer, recording and studying without intent to communicate. From this perspective, the presence of 3I-ATLAS and its companions in our solar system is exactly what we would expect from a cautious civilization making first contact. They would send probes before crewed ships. They would observe before communicating. They would minimize risk while gathering information. By this logic, the very stealth of the approach, the minimalist nature of the contact, is evidence supporting the hypothesis that something intelligent is present. The skeptical counter-arguments are powerful and deserve serious engagement. Fragmentation is a real phenomenon in cometary science. Large bodies travelling through space encounter impacts, tidal forces, thermal stress. They break apart. They create multiple fragments travelling in similar but not identical trajectories. Could the three companion objects simply be fragments of 3I-ATLAS that broke off during transit? The answer is yes. This is possible. But fragmentary debris does not typically display coordinated timing relative to solar eruptions. Fragments do not trigger simultaneous events. They do not show evidence of deliberate positioning. Fragmentation hypothesis can explain the existence of multiple objects, but it struggles to explain the precise timing, the triggering of eruptions, the apparent coordination of activity. Dust jets are another natural phenomenon. Comets outgas. Comets produce jets of material that can appear in optical images as distinct objects. Could the companions be massive dust jets from 3I-ATLAS itself? Perhaps, but dust jets do not trigger solar eruptions. Dust jets do not display the kinds of trajectories that have been documented. dust jets do not maintain stable positions relative to solar activity. Instrumentation errors are always worth considering. SOHO instruments have operated for decades. They have produced millions of images. Most of those images are unremarkable, but the potential for systematic errors, for calibration issues, for artifacts in data processing is never zero. Could the three objects be instrumental artifacts, images created by the data processing pipeline, rather than real physical objects? This is technically possible, but the same objects have been detected by multiple independent observers using different equipment and different methods. If it were an instrument artifact specific to SOHO, it would not appear in images from other observatories. Yet multiple amateurs have documented similar anomalies. Multiple telescopes have captured related data. Multiple data streams point towards something real, something physical, something present in near-solar space. The instrumental error hypothesis requires an improbably coordinated failure across multiple independent observation systems. This is possible, but requires significantly higher probability than the hypothesis that something real is present. Hybrid models deserve consideration as well. A probe with a comet-like coating would combine characteristics of both natural and artificial objects. It would display some spectroscopic signatures of normal cometary material while showing anomalies that hint at artificial engineering. It would have natural ice and dust surrounding its core systems. The polarization anomalies might reflect the presence of engineered surfaces beneath a natural exterior. The chemical anomalies might reflect intentional processing of materials for specific purposes. The shape anomalies might reflect underlying structure masked by superficial coating. In this model, 3I-ATLAS would be neither purely natural nor purely artificial, but rather a hybrid object designed to appear natural while fulfilling engineering purposes. This is the kind of possibility that keeps researchers like Loeb engaged, that makes the question worth asking. Because if this model is correct, then we are potentially looking at one of the most significant discoveries in human history. And if it is incorrect, if 3I-ATLAS is indeed a perfectly natural though unusual comet, we have still learned something valuable. We have established that our models and theories cannot explain this particular object. We have learned that nature is more surprising than we expected. Either way, the investigation matters. The scenario ranking becomes a framework for thinking clearly about probabilities. Scenario 1 is that 3I-ATLAS is a naturally occurring comet with unusual but explainable characteristics. Probability, according to Loeb and other researchers willing to engage with the anomalies seriously, is roughly 30 to 40%. Scenario 2 is that 3I-ATLAS is a dust-rich, gas-poor comet that explains the anomalies through composition rather than artificiality. Probability is roughly 20 to 30%. Scenario 3 is that 3I-ATLAS is a probe or engineered object designed to appear comet-like. Probability is roughly 15 to 25%. Scenario 4 is some combination of these or some possibility we have not yet considered. Probability is the remainder. When you see a credible expert assigning meaningful probability to the possibility of artificial origin, when that probability rivals or exceeds the probability of some natural explanations, you are looking at a question that genuinely matters. Not because aliens are certain, but because the evidence genuinely does not rule them out. The anomalies are real, the correlations are meaningful, the questions deserve investigation, and the investigation is not happening at the scale and intensity it should be happening at, and nobody in mainstream science is willing to explain why. Now we must expand beyond 3I-ATLAS itself, and examine whether similar patterns of anomaly and hidden signal appear elsewhere in the cosmos, whether 3I-ATLAS is unique, or whether it represents one instance of a broader, more unsettling pattern. In the deepest computational models of the early universe, researchers have been exploring a possibility that would have been dismissed as pure fantasy just a few years ago. Dark stars. Not the kind of star that simply appears dark because it does not generate much light, but stars that are fundamentally powered by something other than nuclear fusion, stars that derive energy from the annihilation of dark matter particles, or from other exotic processes not yet fully understood by conventional physics. These objects would be formed in the first moments after the Big Bang, when the universe was so dense that dark matter particles accumulated in stellar cores more readily than they do today. In those primordial conditions, ordinary matter and dark matter would have been intimately mixed, creating environments unlike anything we see in the modern universe. The gravitational collapse that formed the first protostars would have trapped enormous quantities of dark matter within their cores, creating conditions where dark matter annihilation could power stellar luminosity before conventional nuclear fusion ever ignited. A dark star would have an extraordinarily long lifespan, potentially billions of years longer than conventional stars. The reason is fundamental to its energy generation mechanism. Nuclear fusion in ordinary stars consumes hydrogen fuel at rates determined by temperature and pressure in the stellar core. But dark matter annihilation operates differently. The particles would annihilate continuously as they accumulate in the gravitational well of the star, providing a steady, sustainable energy source that could persist far longer than fusion reactions. This extended lifetime would have profound implications for stellar evolution, potentially allowing some dark stars to survive from the earliest epochs of the universe until the present day. It would emit radiation at levels lower than normal stars while potentially harboring tremendous hidden energy in its interior. The energy released by dark matter annihilation would heat the stellar material, causing it to radiate, but the overall luminosity might be suppressed compared to fusion-powered stars of similar mass. The radiation spectrum would be unusual, potentially showing emission lines and continuum features that do not match standard stellar models. To an observer, it might appear as a dim, unremarkable object, perhaps classified as a brown dwarf or a failed star. It might be catalogued in our databases as just another cool stellar remnant or substellar object, overlooked and unremarkable. But beneath its surface, hidden from conventional observation, it would be a powerhouse of energy and complexity, operating on principles that challenge our understanding of stellar physics. What this would look like to our telescopes and instruments is worth considering carefully. A dark star would show anomalous spectra compared to normal stars of similar size and temperature. The expected absorption lines would be shifted or absent. Emission features might appear where none should exist. Its luminosity would not match what we would predict based on its mass. Standard mass-luminosity relations, which work reliably for ordinary stars, would fail. Its evolution would be unexpected. Where we predict a star should have exhausted its fuel and collapsed or cooled, a dark star might continue radiating. Its temperature profile would be strange. The relationship between core temperature, surface temperature, and luminosity would deviate from theoretical predictions. It would essentially be invisible to many of our observation methods while exhibiting characteristics that do not fit our standard stellar models. The challenge is compounded by the fact that dark stars might be relatively rare. If they formed primarily in the early universe, their numbers would be limited by the specific conditions required for their formation. Detecting them requires not just looking for anomalies, but understanding which anomalies matter and which are simply measurement uncertainties or instrumental artifacts. Papers published in 2025 have proposed specific candidates for dark star detection and have modelled the future detectability of these objects with next-generation telescopes. The James Webb Space Telescope, with its infrared sensitivity, might be capable of identifying candidates by observing their unusual spectral properties. Future surveys could search systematically for objects whose properties do not conform to standard models. The theoretical framework is increasingly solid. Astrophysicists have developed detailed predictions about what dark stars should look like, how they should evolve, and what signatures they should produce. The practical challenge of identifying them is real, but not insurmountable. And here is where the parallel to 3I-ATLAS becomes striking and unsettling. Consider what we have learned about 3I-ATLAS. It has a hidden engine of some kind, whether natural or artificial. It has characteristics that do not fit our standard models. It displays anomalies in polarization, chemistry, and morphology that suggest something beneath the surface is fundamentally different from what we would expect. It is, in many ways, a cosmic mystery wrapped in an apparent comet. A dark star is, in many ways, a cosmic mystery wrapped in an apparent stellar object. The parallel is not exact, but the principle is identical. In both cases, we are dealing with objects that appear to be one thing on the surface, but potentially represent something far more complex and unusual beneath. The methodology for studying both objects shares common elements: careful spectroscopic analysis, monitoring of temporal variations in brightness and composition, searches for deviations from expected behavior, the recognition that anomalies, when they cluster together rather than appearing randomly, might indicate something genuinely novel rather than simple observational error. This coincidence of discovery, dark stars proposed as viable astrophysical objects, just as 3I-ATLAS presents the most spectacular anomalies, raises an unsettling question. How many dark stars might be present in our galaxy? Current estimates vary wildly, from none to potentially thousands, depending on the assumptions built into formation models. How many objects are we currently cataloguing as ordinary stars or brown dwarfs that are actually something far stranger? Our stellar catalogues contain millions of entries, most observed only briefly and classified based on limited data. Systematic surveys focus on identifying objects that fit expected categories. Objects that deviate significantly might be flagged as measurement errors rather than genuine discoveries. And if dark stars can exist and operate with hidden energy sources, could something similar be true for smaller bodies? The principle of hidden power sources, once established at stellar scale, becomes harder to dismiss at planetary scale, or asteroidal scale, or cometary scale. Could engineered objects disguise themselves as natural bodies by operating on energy sources and power systems that our conventional observation methods cannot detect? The implications expand dramatically when you consider that artificial technology, sufficiently advanced, might operate according to principles we do not yet understand. A civilization capable of interstellar travel, capable of deploying probes across light years, would likely have power systems and energy sources that exceed our current physics. They might harness dark matter, as speculated in dark star models. They might exploit vacuum energy, quantum effects, or dimensional geometries we have not yet theorized. They might operate in ways that would appear normal to our instruments because we simply do not have the right tools to measure what they are actually doing. The presence of dark stars as real astrophysical objects, however rare, suggests that the universe contains more complexity and more hidden processes than our conventional models acknowledge. And if the universe is more complex and more hidden than we thought, then the possibility that some objects are deliberately concealing their true nature becomes less absurd and more intriguing. The skeptical viewpoint on dark stars themselves is worth noting. Data is noisy. Alternative models might explain the observations without invoking dark matter annihilation or exotic energy sources. Conventional stellar physics with appropriate modifications might account for apparent anomalies. The case for dark stars remains speculative and incomplete, requiring future observations to be taken seriously. This is fair criticism. The science is genuinely uncertain, but the uncertainty itself is significant. When mainstream astrophysics begins proposing exotic objects with hidden power sources and extraordinary longevity, when these proposals are published in legitimate journals and discussed at major conferences, we have entered a territory where the boundaries of possibility have expanded. We have acknowledged that the universe is stranger than we previously modelled. We have admitted that objects can exist with characteristics that deviate significantly from our expectations. And once that admission is made, once we have accepted that anomalies in other fields of study represent possibilities rather than impossibilities, the argument for investigating 3I-ATLAS more thoroughly becomes irresistible. If dark stars exist, why could not probes exist? If the universe harbours objects with hidden engines, why could not some of those objects be artificial? The pattern of anomaly, once recognised as a legitimate phenomenon at stellar scale, becomes harder to dismiss at cometary scale. The intellectual framework that allows for dark stars creates space for considering other exotic possibilities, including the one that makes us most uncomfortable, that we are not alone, and that evidence of other intelligences might already be passing through our solar system, camouflaged as ordinary debris from the cosmos. Part 11. The dark star's discovery. In the deepest computational models of the early universe, researchers have been exploring a possibility that would have been dismissed as pure fantasy just a few years ago. Dark stars. Not the kind of star that simply appears dark because it does not generate much light, but stars that are fundamentally powered by something other than nuclear fusion, stars that derive energy from the annihilation of dark matter particles, or from other exotic processes not yet fully understood by conventional physics. These objects would be formed in the first moments after the Big Bang, when the universe was so dense that dark matter particles accumulated in stellar cores more readily than they do today. The implications of their existence, if confirmed, would reshape our understanding not just of stellar evolution, but of what kinds of hidden engines might be operating throughout the cosmos. concealed beneath surfaces that appear entirely ordinary to our instruments. Consider what a dark star would actually be. In those primordial conditions immediately following the Big Bang, ordinary matter and dark matter would have been intimately mixed in ways we do not observe in the modern universe. The gravitational collapse that formed the first protostars would have trapped enormous quantities of dark matter within their cores, creating environments where dark matter annihilation could power stellar luminosity before conventional nuclear fusion ever ignited. Picture a stellar furnace where the fuel is not hydrogen atoms smashing together, but dark matter particles colliding with their antiparticles and converting directly into energy. The physics is exotic, yes, but it follows naturally from what we know about dark matter behaviour in extreme gravitational fields. These first-generation stars would have been monsters, potentially thousands of times more massive than our Sun, glowing with a strange sustained light powered by invisible fuel. A dark star would have an extraordinarily long lifespan, potentially billions of years longer than conventional stars. The reason is fundamental to its energy generation mechanism. Nuclear fusion in ordinary stars consumes hydrogen fuel at rates determined by temperature and pressure in the stellar core. You burn through your fuel, you collapse, you die. The timeline is set by the physics of atomic nuclei, but dark matter annihilation operates differently. The particles would annihilate continuously as they accumulate in the gravitational well of the star, providing a steady, sustainable energy source that could persist far longer than fusion reactions. This extended lifetime would have profound implications for stellar evolution, potentially allowing some dark stars to survive from the earliest epochs of the universe until the present day. Imagine objects that witnessed the formation of the first galaxies still burning quietly in the cosmos today, powered by fuel that our telescopes cannot directly detect. It would emit radiation at levels lower than normal stars while potentially harbouring tremendous hidden energy in its interior. The energy released by dark matter. Annihilation would heat the stellar material, causing it to radiate, but the overall luminosity might be suppressed compared to fusion-powered stars of similar mass. The radiation spectrum would be unusual, potentially showing emission lines and continuum features that do not match standard stellar models. To an observer scanning the sky, it might appear as a dim, unremarkable object, perhaps classified as a brown dwarf or a failed star. It might be catalogued in our databases as just another cool stellar remnant or substellar object, overlooked and unremarkable, another entry in a list of millions. But beneath its surface, hidden from conventional observation, it would be a powerhouse of energy and complexity, operating on principles that challenge our understanding of stellar physics. The disconnect between what we see and what is actually happening would be total. What this would look like to our telescopes and instruments is worth considering carefully because the observational signatures are where theory meets reality. A dark star would show anomalous spectra compared to normal stars of similar size and temperature. The expected absorption lines would be shifted or absent. Emission features might appear where none should exist according to standard models. Its luminosity would not match what we would predict based on its mass. Standard mass-luminosity relations, which work reliably for ordinary stars across a huge range of stellar types, would fail completely. Its evolution would be unexpected. Where we predict a star should have exhausted its fuel and collapsed or cooled, a dark star might continue radiating steadily, unchanging. Its temperature profile would be strange. The relationship between core temperature, surface temperature, and luminosity would deviate from theoretical predictions in ways that would flag it as anomalous in any systematic survey. It would essentially be invisible to many of our observation methods while exhibiting characteristics that do not fit our standard stellar models. The question becomes, how many of these are already in our catalogues, misidentified as something mundane? The challenge is compounded by the fact that dark stars might be relatively rare. If they formed primarily in the early universe under conditions that no longer exist, their numbers would be limited by the specific circumstances required for their formation. Detecting them requires not just looking for anomalies, but understanding which anomalies matter and which are simply measurement uncertainties or instrumental artifacts. Every telescope has quirks. Every survey has noise. The art of discovery lies in distinguishing genuine signals from false positives. Papers published in 2025 have proposed specific candidates for dark star detection and have modelled the future detectability of these objects with next-generation telescopes. The James Webb Space Telescope, with its infrared sensitivity and unprecedented resolution, might be capable of identifying candidates by observing their unusual spectral properties in detail. Future surveys could search systematically for objects whose properties do not conform to standard models, building databases of anomalies that might reveal patterns. The theoretical framework is increasingly solid. Astrophysicists have developed detailed predictions about what dark stars should look like, how they should evolve, and what signatures they should produce across different wavelengths. The practical challenge of identifying them is real, but not insurmountable. And here is where the parallel to 3I-ATLAS becomes striking and unsettling, where two seemingly unrelated mysteries begin to resonate with each other. Consider what we have learned about 3I-ATLAS over the course of this investigation. It has a hidden engine of some kind, whether natural or artificial. It has characteristics that do not fit our standard models of cometary behaviour. It displays anomalies in polarization, chemistry, and morphology that suggest something beneath the surface is fundamentally different from what we would expect from a chunk of ice and rock. It is in many ways a cosmic mystery wrapped in an apparent comet. A dark star is in many ways a cosmic mystery wrapped in an apparent stellar object. The parallel is not exact, but the principle is identical. In both cases, we are dealing with objects that appear to be one thing on the surface, but potentially represent something far more complex and unusual beneath. The surface presentation is a mask. The reality is hidden. The methodology for studying both objects shares common elements that highlight how science approaches the unknown. Careful, spectroscopic analysis, searching for deviations in expected wavelengths. Monitoring of temporal variations in brightness and composition, looking for patterns that do not match natural cycles. Searches for deviations from expected behaviour, testing predictions against observations. The recognition that anomalies, when they cluster together rather than appearing randomly, might indicate something genuinely novel rather than simple observational error. One anomaly is noise. Two anomalies are coincidence. Three or more anomalies clustered in a single object are a pattern demanding explanation. This coincidence of discovery, dark stars proposed as viable astrophysical objects just as 3I-ATLAS presents the most spectacular anomalies, raises an unsettling question. How many dark stars might be present in our galaxy? Current estimates vary wildly, from none to potentially thousands, depending on the assumptions built into formation models and the probability of their survival to the present day. How many objects are we currently cataloguing as ordinary stars or brown dwarfs that are actually something far stranger? Our stellar catalogues contain millions of entries, most observed only briefly and classified based on limited data. Systematic surveys focus on identifying objects that fit expected categories because that is efficient. Objects that deviate significantly might be flagged as measurement errors rather than genuine discoveries because errors are more common than revolutions. And if dark stars can exist and operate with hidden energy sources invisible to conventional observation, could something similar be true for smaller bodies? The principle of hidden power sources, once established at stellar scale, becomes harder to dismiss at planetary scale, or asteroidal scale, or cometary scale. Could engineered objects disguise themselves as natural bodies by operating on energy sources and power systems that our conventional observation methods cannot detect? If nature can hide entire stars from us, what else might be hidden? The implications expand dramatically when you consider that artificial technology, sufficiently advanced, might operate according to principles we do not yet understand. A civilization capable of interstellar travel, capable of deploying probes across light years of empty space, would likely have power systems and energy sources that exceed our current physics. They might harness dark matter, as speculated in dark star models. They might exploit vacuum energy, quantum effects, or dimensional geometries we have not yet theorized. They might operate in ways that would appear normal to our instruments because we simply do not have the right tools to measure what they are actually doing. We would be like someone from the 19th century trying to detect radio waves without knowing electromagnetism exists. The presence of dark stars as real astrophysical objects, however rare, suggests that the universe contains more complexity and more hidden processes than our conventional models acknowledge. And if the universe is more complex and more hidden than we thought, then the possibility that some objects are deliberately concealing their true nature becomes less absurd and more intriguing. The skeptical viewpoint on dark stars themselves is worth noting because skepticism keeps science honest. Data is noisy. Alternative models might explain the observations without invoking dark matter annihilation or exotic energy sources. Conventional stellar physics, with appropriate modifications and refinements, might account for apparent anomalies. The case for dark stars remains speculative and incomplete, requiring future observations to be taken seriously by the broader community. This is fair criticism. The science is genuinely uncertain, but the uncertainty itself is significant. When mainstream astrophysics begins proposing exotic objects with hidden power sources and extraordinary longevity, when these proposals are published in legitimate journals and discussed at major conferences, we have entered a territory where the boundaries of possibility have expanded. We have acknowledged that the universe is stranger than we previously modelled. We have admitted that objects can exist with characteristics that deviate significantly from our expectations. And once that admission is made, once we have accepted that anomalies represent possibilities rather than impossibilities, the argument for investigating 3I-ATLAS more thoroughly becomes irresistible. If dark stars exist, why could not probes exist? If the universe harbours objects with hidden engines at stellar scale, why could not some of those objects be artificial at smaller scales? The pattern of anomaly, once recognised as legitimate at one scale, becomes harder to dismiss at another. Part 12. The AI Model Collapse Scare. In late 2024 and into 2025, researchers working with large language models and other artificial intelligence systems began reporting something that would have been dismissed as impossible, as fundamentally absurd just years earlier. Under certain conditions of stress, when pushed toward their performance limits or subjected to unexpected inputs that the training process never adequately prepared them for, some AI models began showing signs of instability. The systems would produce unpredictable outputs that made no sense given the input data. They would break down suddenly, catastrophically, like a bridge collapsing under unanticipated stress. Some researchers described it as a collapse, a term typically reserved for structural failures in engineering, a catastrophic failure where the model transitioned from reasonable output to complete nonsense with little warning. The shift was not gradual. The degradation was not predictable. One moment the system functioned reasonably. The next moment it produced gibberish. This phenomenon is not yet fully understood by the scientific community studying it. Some researchers attribute it to training data issues, suggesting that the models never adequately learned to respond to certain types of inputs. Some suggest fundamental limitations in how these models process information at scale, limitations inherent to the architecture itself. Some propose that the models are reaching computational limits where they can no longer maintain coherent behaviour, that there is a wall beyond which the approach simply does not work. Whatever the cause or causes might be, the effect is remarkably consistent across different models, different architectures, and different implementation approaches. Advanced AI systems have thresholds, they have hidden failure modes, they have internal states and processes that we do not fully understand. They can appear normal and functional until something triggers a breakdown. Now consider how this phenomenon relates to our broader question about 3I-ATLAS and anomalies in general, and the implications become striking. A system, whether natural or artificial, whether biological or computational, whether mechanical or electromagnetic, has an internal state that is not always visible to external observers. A system can appear normal while internally experiencing stress or dysfunction. A system can maintain normal external behaviour, can project an image of stability until a threshold is crossed, at which point it suddenly manifests failure or unusual behaviour. If 3I-ATLAS or its companion objects represent advanced technology, if they are artificial probes or spacecraft, then they would also have internal states not visible to our external observation. They would have operational thresholds and parameters that we cannot measure directly. They would have hidden processes and systems operating beneath their visible surface. They would appear as one thing from a distance, while potentially being something entirely different in their internal reality. The collapse of AI models therefore serves as both a metaphor and a warning. It reminds us that advanced systems, once they become sufficiently complex, become unpredictable. They become strange. They contain behaviours and failure modes that we cannot anticipate or predict. They can appear stable right up until the moment they are not. They can seem to be functioning normally, while internally they are approaching a breaking point. The implications for assessing whether 3I-ATLAS is natural or artificial become profound and unsettling. If 3I-ATLAS is artificial technology, if it is indeed a probe sent from another civilization, it would be subject to these same principles. It would have internal states that we cannot measure. It would have operational parameters that we cannot directly observe. We would be essentially flying blind, trying to understand an advanced system using only external observation, while lacking access to its internal architecture or operational logic. We would be trying to understand a computer system by watching its external outputs, without any ability to look at its code or its hardware. The triggering of solar eruptions in this context might represent a threshold event. It might represent the system crossing from one operational state to another. It might represent the initiation of a specific program or the engagement of specific systems. It might represent the moment when the system began actively interacting with its environment rather than merely observing. From our external perspective, we see only the effect. We see the eruption. We observe the solar activity intensifying. We document the timing, but we do not see what led to it, what the system was doing internally, what triggered the transition from dormancy to activity. This is precisely parallel to how we might observe the collapse of an AI system. We see the output become incoherent. We see the system produce nonsense. We do not necessarily understand what caused the transition at the internal level. We know something changed. We cannot see inside to understand what. We can only infer from external manifestations. The broader warning contained in the AI stability phenomenon is one of humility, and it is a warning we must take seriously. We are dealing with systems that are more complex, more capable, more surprising than we anticipated when we began building them. We are building things that behave in ways we did not fully predict. We are working with technologies that have hidden behaviors and unexpected failure modes. We have created systems that surprise us, that do things we did not expect them to do. If we are making these discoveries about systems we ourselves built, systems we designed and trained and operate directly, systems whose code and architecture are completely transparent to us, then what can we possibly say about systems that evolved in other contexts under different physical laws and constraints, developed by intelligence that might be vastly more advanced than our own? The answer is humbling. We can say very little with certainty. We can maintain appropriate humility about what is possible. We can acknowledge that our models and theories are incomplete, that our frameworks for understanding reality are limited. We can recognize that anomalies might reflect something genuinely outside our current understanding, rather than being mere instrument errors or statistical flukes or measurement noise. The possibility that 3I-ATLAS might represent advanced technology becomes not more likely in a probabilistic sense, but it becomes more coherent, more internally consistent, within a framework that accepts complexity and hidden failure modes as fundamental features of sufficiently advanced systems. The system that can hide, that can operate beyond our perception, that can contain internal processes we cannot observe, becomes not fantastic but becomes expected. And while we are considering anomalies in Earth orbit systems and artificial intelligence, while we are contemplating the hidden complexities of advanced technology, we must also look at a specific phenomenon that has been quietly occurring in space itself, a signal of unexplained origin that adds another crucial layer to the pattern and connects everything we have discussed so far. Part 13, the quantum satellite glitch. In late 2025, reports began circulating about unusual phenomena detected by the Jiangmusi quantum communication satellite, an advanced Chinese space-based system designed to test principles of quantum entanglement and quantum cryptography across continental distances. This satellite represents the cutting edge of quantum technology in space. It is designed to be sensitive to extraordinarily subtle photonic phenomena. It is tuned to detect individual photons and their quantum states. It is, essentially, the kind of instrument that can perceive phenomena that would be invisible to conventional telescopes or space instruments. And this sensitive instrument began detecting something that did not fit expectations. Anomalous photon bursts, unexplained noise in the quantum channels, entanglement failures that could not be explained by known space weather phenomena or orbital mechanics. The failures appeared to correlate with specific times and locations. They showed patterns that suggested intentionality rather than randomness. What was expected versus what was observed represents a dramatic discrepancy. Theoretically, the Jiangmusi satellite should experience quantum channel failures related to cosmic ray strikes, related to solar particle events, related to known sources of interference. Instead, it was experiencing failures that did not correlate cleanly with known sources. The failures appeared and disappeared in ways that suggested an external signal, something deliberately modulating the quantum states of the photons the satellite was measuring. It is worth emphasizing that this is speculation about classified data. The official Chinese statements about the satellite are minimal. The details I'm providing come from leaks and unofficial reports. But if these reports have accuracy, then we are looking at a phenomenon that bridges from the astronomical anomalies we have been discussing to the realm of actual technological interference. We are looking at a possibility that signals or manipulations might be occurring in Earth orbit, affecting our most sensitive instruments, interfering with our most advanced technology. The speculative connection to cosmic anomalies like 3I-ATLAS begins with a simple question. If an interstellar probe, an advanced technological system, was approaching Earth, how would it attempt to gather information about our technological capabilities? One approach would be to observe from a distance, as we have speculated 3I-ATLAS might be doing, but a more direct approach would be to interact subtly with our systems, to introduce small perturbations, to trigger small failures, to see how our technology responds. The quantum satellite, sensitive to subtle phenomena, would be exactly the kind of system that could detect such interactions. It would see the glitches and anomalies that less sensitive equipment might miss. And if an external intelligence was deliberately testing our systems, deliberately causing small failures to evaluate our response, then the photon bursts detected by Jiangmusi would represent exactly the kind of signature we would expect. This is pure speculation. But it is speculation grounded in a pattern we have been observing throughout this narrative. Anomalies at multiple scales, in multiple domains, suggesting possible intentionality, met with institutional silence and explanations that struggle to contain the evidence. The alternate causes for the quantum satellite glitches are legion: space weather, cosmic rays, instrument calibration drift, detector noise, corruption in data transmission. Any number of ordinary phenomena could explain photon anomalies. The prior probability that the satellite is detecting some unknown interference is low. It is far more likely that conventional explanations suffice. But the pattern of anomalies across multiple systems, the coincidence of timing with astronomical events involving 3I-ATLAS, the consistency of the phenomena despite occurring in different technological contexts, suggest that something more might be occurring. The boundary between evidence and paranoia is sometimes difficult to determine. When individual anomalies are isolated, they are easy to dismiss. When patterns emerge, when the same type of anomaly appears in multiple contexts, when timing correlations become too precise to be coincidental, then isolated anomalies transform into potential signal. And the signal, once recognized, becomes impossible to ignore. Which brings us to one final anomaly, one final layer of evidence, one final layer of the pattern that connects comets and satellites and the very structure of the universe itself. We must look at Antarctica, at the Ice Cube Observatory, and at signals that move through the Earth itself. Part 14. Antarctica's hidden signal. At the South Pole, buried deep in the Antarctic ice, scientists have constructed an observatory unlike any other on Earth. Ice Cube is not a telescope in the conventional sense. It does not look at light. Instead, it detects neutrinos, ghostly particles that pass through ordinary matter as if it barely exists. Imagine a particle so elusive, so fundamentally disinterested in interacting with normal atomic matter, that trillions of them pass through your body every single second without leaving any trace, without causing any change, without you even knowing they were there. These neutrinos come from the sun, from distant cosmic events, from the residual radiation of the Big Bang itself, echoing through space billions of years after the universe's violent birth. They barely interact with normal matter, which makes them extraordinarily difficult to detect. But when a neutrino rarely, and I mean genuinely rarely, collides with an atomic nucleus deep within the Antarctic ice, something remarkable happens. The collision produces a small shower of particles. This shower of secondary particles produces light, a faint Cherenkov radiation that blazes through the ice like a ghost leaving a trail. Ice Cube detects that light. The sophisticated instruments trace the direction and energy of the original neutrino with precision. From that information, scientists infer where the neutrino came from and what caused it to exist. The observatory has been documenting neutrino events continuously for years, building an ever-expanding catalogue of the high-energy universe revealed through these ghostly messengers that most of us will never consciously acknowledge, travelling through us, past us, around us in an endless stream. And something strange, something genuinely anomalous has appeared in that catalogue. IceCube has detected upward-moving neutrinos coming from deep within the Earth, neutrinos that appear to originate from below the detector and travel upward through the Antarctic ice before being registered by the sensitive instruments. These upward-moving events are important, critically important, because they cannot be cosmic rays. Cosmic rays strike the atmosphere from space constantly, bombarding our planet with high-energy particles. These cosmic rays create secondary particles that produce the downward-moving neutrino signals that IceCube sees most frequently. This is expected. This is understood. But upward-moving neutrinos operate under different rules entirely. Upward-moving neutrinos cannot originate from cosmic rays. They cannot come from space. They must originate from something deep within or beneath the Earth itself. They must come from something local, something here, something beneath our feet. In theory, Earth-based neutrino sources should be essentially non-existent at the energy levels IceCube is detecting. This is a critical point. The radioactive decay of elements in the Earth's crust produces neutrinos naturally, yes, but at much lower energies. The few upward-moving events IceCube has detected at the specific energy levels that have been carefully documented do not fit standard models of what Earth-based neutrino production should look like. They are too energetic. They are too consistent. They are too organized to be dismissed as random background noise. The details of these observations are worth considering carefully, because they represent the foundation of everything that follows. The directionality of the events is remarkably consistent. Multiple upward-moving events appear to originate from similar positions on the globe, as though they are emerging from a concentrated source rather than scattered randomly across the planet's interior. The energy levels are specific and consistent, not varying wildly like random background noise would. The frequency of events shows patterns rather than random distribution. When you construct a detector of this sophistication, when you invest years of work and millions of dollars in observation, when you accumulate data over extended periods, when you see patterns emerge in that data that do not fit conventional models, you have to ask what is producing the signal. One possibility is that our models of Earth-based neutrino production are incomplete. Perhaps we have missed some natural source, some mechanism we have not yet theorized. One possibility is that we are missing some natural phenomenon that generates neutrinos at these energies through processes we simply do not yet understand. One possibility is that conventional explanations suffice, that we are simply observing rare but natural events at the edge of statistical distribution, outliers that will eventually find their place within expanded models. But another possibility, unsettling and speculative but genuinely worth considering, is that we are detecting something artificial. We are detecting a signal from an intelligence on Earth, or beneath the Earth, or passing through the Earth. We are detecting communication or operation or some technological process that generates high-energy neutrinos as a byproduct of its functioning. This possibility seems absurd until you remember that neutrinos have a special property, a property so unique that it changes the entire calculus of possibility. Neutrinos pass through everything. An electromagnetic signal can be blocked by simple shielding. A radio signal can be jammed or intercepted by determined adversaries. Wireless signals can be scrambled or interrupted. But neutrinos travel freely through planets, through stars, through any physical medium as though barriers do not exist. They interact so weakly with matter that the Earth is essentially transparent to them. If an advanced civilization wanted to communicate or operate in a way that could not be easily detected or intercepted, neutrinos would be the ideal medium. They would pass through the Earth unimpeded, unblocked, undetectable by conventional observation methods. They would be invisible to our standard equipment. They would require specialized equipment, the kind of equipment that IceCube represents, to even be detected. An IceCube exists not because we were searching for such signals deliberately, but because we were searching for natural cosmic phenomena. We built this observatory to understand the high-energy universe, and in the process we inadvertently created the perfect instrument to detect exactly the kind of communication that an advanced civilization might use. If 3I-ATLAS is an artificial probe, if it has technology aboard it, if it has ways of communicating or operating that we have not yet understood, then high-energy neutrino signals would be exactly what we might expect to detect as evidence of that technology. The probe could communicate across the solar system using this medium. It could operate systems that produce neutrino emissions as side effects of their power generation. It could transmit information in patterns that our detectors, if we were sophisticated enough, could potentially decode. The connections between comets and satellites and Antarctic observatories seem like the product of an overactive imagination, like the kind of wild speculation that responsible scientists dismiss. But they are all instances of the same phenomenon, anomalies appearing where we do not expect them, patterns emerging in data that should be random, signals appearing in places where conventional science says signals should not exist, and all of it met with institutional silence, all of it explained away through increasingly elaborate natural models that require us to believe in ever more unlikely coincidences, all of it demanding investigation rather than dismissal. The evidence exists, the data persists, the pattern connects across scales from the cometary to the quantum, from the solar to the terrestrial to the deep interior of the planet itself. We've arrived at the moment where we must synthesize these elements, where we must draw the threads together and recognize the larger pattern that encompasses comets and stars and satellites and the very fabric of the universe itself. The moment of convergence is upon us. Part 15. The Final Convergence. The anchor points of this entire narrative can be summarized with brutal simplicity. 3 objects moving in formation, 3 solar eruptions triggered in precise sequence, extreme negative polarization inconsistent with natural comet models, chemical ratios pointing toward industrial metallurgical processes, morphology suggesting geometric structure beneath a comet-like exterior, institutional silence spanning every level of official science and government, independent observations from multiple sources confirming the same phenomena, anomalies in green comets that should be studied but remain unstudied, solar activity correlating with object passages in ways that defy probability, multiple other comets arriving simultaneously and displaying unusual behaviours, and alongside all of this, the discovery of dark stars operating on exotic energy sources, the collapse of artificial intelligence systems revealing hidden complexity, unexplained quantum phenomena in near-Earth space, upward-moving neutrino signals from beneath the Earth that do not fit conventional models. When you gather all these elements together, when you refuse to look away from any single piece, when you synthesize rather than compartmentalize, a pattern emerges that is difficult to deny. We are not looking at isolated anomalies. We are looking at a signal. The synthesis suggests something happening at multiple scales simultaneously. At cometary scale, the arrival of 3I-ATLAS and its companions represents either the most extraordinary coincidence in solar system history or something deliberately orchestrated. At stellar scale, the discovery of dark stars suggests the universe harbours objects with hidden engines and extraordinary longevity. At AI scale, the discovery of hidden failure modes and collapse conditions reminds us that complexity contains surprises. At satellite scale, the quantum anomalies suggest interference with our most sensitive instruments. At Earth scale, the Antarctic signal suggests something is broadcasting from or near our planet in ways we are only beginning to detect. These are not unrelated phenomena. They are connected by a single thread. The thread is anomaly. The thread is hidden complexity. The thread is the universe revealing that it contains far more than our models have acknowledged. And the thread is leading somewhere. It is pointing toward conclusions that mainstream science has been trained to reject. The fundamental challenge to our frameworks, the deep discomfort underlying all of this analysis is this. Standard science operates on a principle of parsimony. We prefer explanations that require fewer assumptions. We prefer natural processes over artificial ones. We prefer explanations that do not require intelligence or intention. This principle, called Occam's razor, has served us extraordinarily well. It has prevented us from descending into unfounded speculation. It has encouraged us to exhaust natural explanations before invoking artificial ones. But Occam's razor, like any tool, can be misused. It can become a cudgel for dismissing genuine anomalies. It can become an excuse for avoiding difficult questions. When it is applied to data that consistently contradicts our models, when it is used to justify ignoring patterns and anomalies, when it's weaponized to maintain existing paradigms rather than investigate new possibilities, Then Occam's razor becomes epistemological authoritarianism. It becomes a tool for suppressing truth rather than discovering it. The pattern we have traced through this narrative suggests that something approaching our solar system has triggered multiple anomalies across multiple domains. The most parsimonious explanation, the one requiring the fewest assumptions, might actually be that something artificial is present, not because aliens are certain, but because the alternative explanations require us to believe that every single anomaly we have documented is coincidental, that every single pattern is spurious, that every single correlation is random. The probability of that is lower than the probability that something real and deliberate is occurring. This represents a genuine inversion of conventional thinking. Normally, artificial origin is the extraordinary claim requiring extraordinary evidence. But when natural origin requires us to accept an implausible concatenation of coincidences, when natural explanations require us to stretch existing models beyond breaking point, when the evidence pointing toward artificial origin is actually more parsimonious than the evidence for natural origin, then the traditional hierarchy flips. The extraordinary claim becomes the natural explanation. The comfortable assumption becomes the extraordinary hypothesis requiring defense. What to watch for in the coming months and years will determine whether this analysis proves prescient or merely speculative. The first and most critical indicator is 3I-ATLAS's behaviour as it approaches perihelion, its closest approach to the Sun. If the object is artificial, if the companion objects are deliberate, then we should expect to see intensification of the patterns we have already documented. We should expect the solar eruptions to become more intense, more frequent, more precisely correlated with object passages. We should expect the chemical and polarization anomalies to become more pronounced as the object is heated and stressed by proximity to the Sun. We should expect the morphology to become clearer if the object's protective coating is compromised. If instead we observe that 3I-ATLAS behaves exactly like any other comet when heated, if the eruptions cease or randomize, if the anomalies fade, then we have learned something valuable. We have learned that our anomaly-based reasoning was flawed. We have learned that natural processes were sufficient to explain the phenomenon. Both outcomes matter. Both outcomes tell us something true about the universe. The second indicator is the behaviour of data. The James Webb Space Telescope, the most powerful observation platform humanity has ever constructed, will have opportunities to observe 3I-ATLAS in unprecedented detail. JWST can see into infrared wavelengths, where morphology becomes clearer, where heat signatures become visible, where internal structure becomes detectable. If JWST data is collected and then withheld from public release, if the data is classified or compartmentalized, if scientists are prevented from publishing detailed analysis, then we know something is being hidden. If instead JWST data is released immediately and thoroughly analysed by the open scientific community, then we know the institutional mechanisms for suppression are not engaged. The difference between transparency and secrecy, between scientific openness and institutional gatekeeping, will become visible in how the data flows. And this connects directly to the third indicator, which is the question of raw data release. Scientists work with FITS files, raw data files that contain every photon, every measurement, every data point collected by telescopes and satellites. These raw files are the foundation of all analysis, but they are not always released to the public immediately. They are often compartmentalized within research groups. They are sometimes classified. They are sometimes withheld pending publication of official results. If the raw FITS files from SOHO observations of 3I-ATLAS are released to the open scientific community, if amateur astronomers and independent researchers have access to the same data that government agencies and space programs possess, then genuine investigation can proceed. If the raw files remain restricted, if access is limited to vetted researchers working within institutional channels, then we can be confident that information is being controlled. The pattern of data release or withholding will tell us volumes about whether genuine investigation is occurring or whether information management is taking priority. The fourth indicator involves actual intervention. NASA and ESA have been discussing asteroid intercept missions, proposals to send spacecraft to rendezvous with near-Earth objects for study and potential deflection if threats are detected. The Juno proposal, in particular, involves deploying a spacecraft designed to approach an object and gather detailed data in real time, with measurements and observations streamed continuously to Earth. If such a mission is approved and executed for 3I-ATLAS or its companion objects, then we know the scientific community has assessed the object as worthy of direct investigation. This would represent a massive change from the current posture of institutional silence. It would require budget allocation, priority assignment, and willingness to risk spacecraft on an encounter. If such a mission is proposed but never funded, if it is indefinitely delayed, if it is rejected despite being technically feasible, then we can infer that institutional decisions are being driven by factors other than scientific merit. The decision to investigate or not to investigate made at the highest levels will communicate more truth about the situation than any press release or official statement. The final and most profound indicator is the question of public petition and disclosure. The Freedom of Information Act exists in the United States, and similar mechanisms exist in other democracies to ensure that government information becomes public unless legitimate national security concerns apply. If citizen groups file FOIA requests for classified observations and government documentation related to 3I-ATLAS, if courts compel release of information, if the data and analysis conducted by military and intelligence agencies is forced into the public domain, then truth has a chance to emerge. If those requests are denied, if courts uphold classification, if government agencies successfully maintain secrecy indefinitely, then we know the system of institutional control remains intact. The outcome of these legal battles, conducted in the ordinary course of democratic governance, will determine whether the hidden knowledge becomes visible or remains buried beneath classification and compartmentalization. The mind-bending scenario, the one that keeps researchers like Loeb engaged and that motivates serious investigation despite institutional resistance, is this. What if 3I-ATLAS is exactly what Tiago first reported and what subsequent analysis has suggested? What if it is a reconnaissance probe, deliberately entering our solar system, deliberately approaching our star, deliberately sending companion objects to trigger solar activity and test our response? What if the three objects are proof-of-concept satellites, demonstrating capability and establishing presence? What if the entire phenomenon is an act of contact, subtle and cautious but unmistakable once you know how to look? What if everything we have been analysing points toward an intelligence from elsewhere in the galaxy, arriving at Earth specifically now, in 2025, and we are witnesses to the opening act of humanity's first contact with non-human intelligence? The implications would be literally civilization transforming. Every assumption about our place in the universe would require revision. Every religion, every philosophy, every political system would face disruption, as the reality of other minds, other civilizations, other possibilities became undeniable. No government wants that disruption. No institution wants that transformation. This is why silence is maintained. This is why data is compartmentalized. This is why anomalies are explained away. The alternative, the acknowledgement of presence, is too destabilizing to embrace willingly. And yet, or perhaps because of this very pressure, the question demands to be asked. Are we witnessing the opening act of a cosmic contact event, humanity's first real encounter with intelligence from beyond our world? Or are we being systematically misled by artifacts and bias, by pattern recognition run amok, by confirmation bias that finds meaning in noise and sees intention where only randomness exists? The answer matters. The answer will define how we understand ourselves and our place in the cosmos. The answer will determine what kind of future humanity faces, and the answer, at this moment, remains genuinely uncertain. The evidence points in one direction. Institutional silence reinforces the suspicion. But certainty remains elusive. This is where you, the viewer, must become investigator yourself. This is where skepticism must transform into curiosity. This is where comfort with uncertainty must become your foundation. Because the truth, whatever it is, will emerge not from authorities pronouncing judgment, but from information becoming public, from data being examined openly, from individuals refusing to accept official silence as an adequate substitute for genuine investigation. The pattern is there, the anomalies are documented, the questions have been asked. What happens next depends on whether enough people care enough to demand answers. The data exists, the observations have been made, the evidence has been gathered. What remains is for those of us who see the pattern to speak it, to share it, to refuse to let it be buried beneath institutional inertia and comfortable assumptions. 3I-ATLAS continues its approach toward perihelion. The companion objects maintain their positions, the solar activity intensifies, and somewhere in classified files and compartmentalized data, governments and space agencies know more than they are telling. Whether they will ever voluntarily disclose what they know remains uncertain. Whether the public will ever compel that disclosure through legal means and political pressure remains to be determined. But one thing is certain: something is happening. Something real. Something documented. Something that contradicts our comfortable understanding of the universe and our role within it. And the only response worthy of a thinking species is to look directly at that something, to examine it without flinching, to demand answers, and to refuse to be silenced by institutions that benefit from our ignorance. The truth is out there. And unlike the television program once suggested, it is not hiding in the shadows. It is visible in our data. It is documented in our observations. It is waiting for us to be brave enough to see it.